Welcome friends, Igor is here, and in this video we will establish several interesting properties of non-singular matrices. In this lesson we will show that the null space of a non-singular matrix is trivial. We will prove that non-singular coefficient matrices always result in unique solutions for the linear systems. And we will start a collection of equivalent statements about non-singular matrices. Let's get started. First, let's observe that a square matrix is non-singular if and only if its null space is trivial. In fact, this is nothing but translation of the appropriate definitions. First, the definition of a non-singular matrix says that this condition is equivalent to the homogeneous linear system with this matrix as the coefficient matrix having only the trivial solution. On the other hand, the null space of the matrix A is the solution set of the homogeneous linear system with A as the coefficient matrix. And now, if you put these two definitions together, you will see that a matrix is non-singular if and only if its null space contains only the zero vector. Next, we are going to establish a remarkable property of non-singular matrices. A square matrix A is non-singular if and only if the linear system with A as the coefficient matrix has a unique solution for all possible vectors of constants. The statement of the theorem contains an if and only if statement, and this means there are two implications for us to prove. First of all, if a matrix A is non-singular, then the linear system with A as the coefficient matrix has a unique solution for every possible vector of constants. And second, in the opposite direction, if the linear system with A as the coefficient matrix has a unique solution for every possible vector of constants B, then A must be a non-singular matrix. The proof for the reverse implication is in fact trivial. So let's assume that the linear system with A as the coefficient matrix has a unique solution for all possible vector of constants B. Because this is true for all possible vectors B, in particular it is true when B is the zero vector. This means that the homogeneous linear system with A as the coefficient matrix has a unique solution. But this is precisely what it means for the matrix A to be non-singular. It is the forward implication in this theorem that is of special interest. Before we get to proving it, let's pause for a second and understand what's the meaning of this statement. We are going to assume that A is a non-singular matrix. In effect, it means we are saying that the homogeneous linear system with A as the coefficient matrix has a unique solution. But now what we are going to prove is knowing the solution set of the homogeneous linear system allows us to conclude that in fact all linear systems with A as the coefficient matrix have a unique solution. We assumed that A is a non-singular matrix, and we already proved that the reduced row echelon form of a non-singular matrix is the identity matrix. This implies that there exists a sequence of row operations that transforms the matrix A into the identity matrix. Let's look at the augmented matrix of the linear system with A as the coefficient matrix and an arbitrary vector of constants B. Because A is a square matrix of size n by n, the augmented matrix has n rows and n plus 1 columns. Let's think what happens when we reduce the augmented matrix. If you forget for a moment about the last column, which comes from the vector of constants of the linear system, we know that the matrix A reduces to the identity matrix. The identity matrix is a matrix in reduced row echelon form, and every column is a pivot column. So the number of leading ones is equal to n, which is the same as the number of rows in the matrix. But this means there is no more room for leading ones in the augmented matrix, because a matrix with n rows cannot have more than n leading ones. What this shows is that all the leading ones in the reduced row echelon form of the augmented matrix are already contained within the first n columns, which correspond to the coefficient matrix. This means that the reduced row echelon form of the augmented matrix of this linear system is identity matrix, which is the reduced row echelon form of the coefficient matrix, plus an extra column. We don't know exactly what it is, but it is what happens to the original vector of constants b after we perform the necessary sequence of row operations to transform A into the identity matrix. Also observe that a matrix which consists of the identity matrix in the first n columns plus an extra column is automatically a matrix in reduced row echelon form. But now, if you imagine what kind of linear system is represented by this reduced augmented matrix, you will see right away that this is a system that has a unique solution. Moreover, the last column of the reduced augmented matrix is the only solution vector to this system. Thus, the linear system with A as the coefficient matrix and B as a vector of constants has a unique solution, and this argument shows that it is true for all possible vectors B, because there was nothing special about our choice of vector B. This argument works for every possible vector. Now, let's summarize our recent discoveries and make several useful observations. First of all, if you have a linear system with a non-singular coefficient matrix, then no matter what the vector of constants is, the linear system will always yield a unique solution. But to check whether a square matrix has this property, all you have to do is solve just one linear system. Not all of them, just one, the homogeneous linear system. Finally, our last theorem is an if and only if statement, and therefore we can conclude that a matrix A is singular, which is the negation of the statement that a matrix is non-singular if and only if. Now, let's think what is the negation to the statement that the linear system has a unique solution for every possible vector B. The negation is that the linear system does not have a unique solution for some vector B. Be careful. The negation of the statement linear system has a unique solution for all B is not a linear system does not have a unique solution for all B. The negation is the linear system does not have a unique solution for some vectors B. We will be coming back to studying properties of non-singular matrices regularly throughout the rest of the course. And to keep track of our discoveries, we are going to put equivalent statements about non-singular matrices into one big theorem, which is going to be regularly updated and is going to grow to many statements. Suppose we have a square matrix A, then the following statements are equivalent. A is a non-singular matrix. A row reduces to the identity matrix. The null space of the matrix A is trivial, which means it only includes the zero vector, and the linear system with A as a coefficient matrix has a unique solution for all possible vector of constants B. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will define the vector space of column vectors. I will see you later.